In this video, we'll be introduced to the concept of a polynomial function. And so a polynomial function is a function of the form p of x, which is equal to a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, plus all those terms down through a sub 1x plus a sub 0, where a sub n are real numbers and n is a whole number. So we've seen polynomials before, and we've even identified the degree of a polynomial. So the degree of a polynomial function is n, that is its largest exponent, and the leading coefficient is a coefficient of that term with the largest exponent, so that is the value a sub n, provided a sub n is not 0. Some examples that we've already studied: constant functions, linear functions, quadratic functions. Those are all examples of polynomial functions. Now on this page I have a chart, a table, that has a polynomial function, and we're going to talk about the degree of that polynomial function, the leading coefficient of the function, and then we'll name that expression, that function, by some terminology. The first one is f of x equals -1. Well, understand that -1 is equivalent to -1 times x to the 0, because x to the 0 is 1. So the degree of this polynomial function is 0. The leading coefficient is -1. And we say that this is a constant function. Right? There's no variable that's going to change the output value. It is always -1. f of x equals 4x minus 2. This has largest exponent of 1 on the variable, so the degree is 1. The coefficient of that term is 4, and hopefully you recognize this as a linear function. f of x equals -2x squared plus 3x minus 1. This is in standard form. The exponents are decreasing. The largest of those is 2. And the coefficient of that term is -2, and this is, of course, a quadratic when we have an exponent of 2. f of x equals x cubed minus 2x squared minus 11x plus 12. Again, this is in standard form with the exponents decreasing. X cubed is the term with the largest exponent, which tells us the degree is 3, and the coefficient of that term is understood to be 1, and the degree 3 is a cubic function. And then f of x equals 9x to the 4th plus 3x cubed minus 2x squared minus 8x plus 10. This is a 4th degree polynomial, so the degree 4, the coefficient of that term is 9, and this is a quartic polynomial. And then f of x equals -3 times the quantity x minus 4 squared times the quantity 2x plus 1 cubed. Understand this one is different than the others because this one is written in factored form, not expanded form. We could take the time to square x minus 4. We could cube 2x plus 1, which would be 2x plus 1 times 2x plus 1 times 2x plus 1. We'd get a lot of terms, and then multiply that all out. But actually, to find the degree and leading coefficient, it is sufficient to multiply the leading terms of each of those factors. So this would be equivalent to -3, and then if we applied the square, we would get x squared and something else. I don't really care what that something else is right now. And then 2x plus 1, when we cube the 2x, we would get 8x cubed plus something else there. And so when we multiply this out, we would multiply those leading terms of each of the factors to really get -3 times x squared times 8x cubed. Again, there would be a lot of other terms in this polynomial, but this is sufficient to tell us what the degree and leading coefficient are. So if we multiply these monomials, we get -24x to the 5, and again, other terms would follow. So the degree is 5, and the leading coefficient is -24. Now we could see the degree here because of the 2 and the 3. We could actually add those to get the 5. The -24, again, I'd have to figure out what are those terms after I apply the exponents and multiply those coefficients together. And then a fifth degree polynomial is called a quintic. Quintic function. Here is an example where we want to identify the degree and leading coefficient of each polynomial function. Part A is f of x equals 7x cubed minus 6x plus 4x to the 9 plus 5x plus 6. The first thing you need to check is see if this is in standard form, and it is not because our exponents are not descending. So we would rewrite this as 4x to the 9 minus x to the 6 plus 7x cubed plus 5x plus 6. And now the leading term is 4x to the 9, which tells us the degree is 9, and the leading coefficient is 4. And f of x equals 3x times 2x plus 4 times the quantity 5 minus x to the third. We will have to think about expanding this, but again, not multiplying it all out, identifying the product of the leading terms of each of the factors. So this would be 3x times the 2x. There's no exponent to apply to that factor, so 2x is the leading term there. And then the 5 minus x, when we cubed that, the cube on the negative 1x would give us negative 1x cubed. Now understand, 5 minus x cubed is not just cubing the 5 and cubing the negative x. It would be 5 minus x times 5 minus x times 5 minus x. And when you do all of that multiplication, the term that has the highest exponent is this negative x cubed. And so if we multiply those leading terms of each of the factors, 3x times 2x times negative x cubed, we would get a negative 6x to the 5 plus, again, some other terms. Right, we add the exponents on the variables and multiply those coefficients. So the degree is the largest exponent 5, and the leading coefficient is negative 6. Part C, f of x equals 4x cubed times 3x minus 2 times 5x plus 1 all squared. Again, this is in factored form. We identify the leading term of each of those factors and apply any exponent to it. The 3x minus 2 is just a linear factor, so only the 3x is going to be coming out from that. 5x plus 1, that is a square factor, so we would have to square 5x to get 25x squared. And so we've identified the leading term of each of the factors when we multiply those. 4x cubed times 3x times 25x squared. We get 300x to the 3 plus 1 plus 2, which is 6. So that tells us that the degree is 6, and the leading coefficient is 300. Now on this particular screen, what I've done is actually graphed all of the polynomials that we had on the first chart. And so like y is equal to negative 1, f of x equals 4x minus 2, negative 2x squared plus 3x minus 1, and so on. And what I want you to see is just the general shape of the graph of these polynomial functions. Notice that they are continuous in the fact that if I start drawing the graph, I can draw it with one smooth stroke without having to pick up my pencil. There's no holes, there's no gaps in the graph, there's no sharp turns in the graph. So some of them have peaks and valleys, but they're all gentle curves, turning points, so to speak. And so these are the characteristics of the graph of a polynomial function. They are smooth, continuous graphs. They have no sharp turns, holes or breaks in their graphs. The domain of all polynomial functions is a set of all real numbers, or negative infinity to infinity, right? There's no restriction on what value we can plug in to that function. The range of a polynomial function actually depends on the parity of its degree. If the degree is odd, the range is a set of all real numbers. If the degree is even, then the range is of the form negative infinity to some number k with a bracket, or bracket k to infinity for some real number k. Very much like quadratics, right? There was a maximum or minimum value of the entire graph, so the range was not all real numbers. Now in this next example, I just want you to think about, is a given graph the graph of a polynomial function? And so in part A, I have this piecewise defined function actually. So it's a part of a parabola that goes from the left to the point 0, 3 with an open circle. And then it picks up at 0, negative 5 and goes through the point 5, 0, which is a part of a line, and extends. So this one cannot be the graph of a polynomial function because there's breaks and gaps in that particular graph. And in part B, notice that it starts in the second quadrant, goes down to the third to some minimum point, comes back up through the origin, up to some maximum point in the first quadrant, and then goes back down and continues in the fourth quadrant. So because this one is a smooth, continuous graph with no sharp turns, no holes, then this can be the graph of a polynomial function. So this would be yes.